Greetings to you all. I welcome you all again to this course on CFD. Today is the starting of week 4. We will be touching upon important topic, what is known as a finite volume method of discretization. This week we will particularly see diffusion equation in detail, convection and diffusion term in Navier-Stokes equation in detail. We will do initially these in 1D form, then we will get to know how to do in 2-dimensional as well as 3-dimensional. Then we will have a separate detailed working on convection term alone. We learned before convection term is nonlinear in nature, hence a separate treatment is required for convection term. We will talk about convection term treatment in detail with different schemes. Then we will also illustrate with example these methods and show comparison wherever possible. There is a special treatment for near boundary implementation. Near boundary nodes will have to account for boundary condition, and we will see how the finite volume formulation gets rewritten for near boundary accounting. This will complete in detail the finite volume formulation without time derivative term. So, in general we know finite volume method is very much suitable for complex geometry, and what is shown here is just a simple structured mesh arrangement. You see here horizontal lines as well as vertical lines, and wherever they meet is shown by a dot that is supposed to represent node, and here you are seeing a node with control volume surrounding that node, which is shown by dotted horizontal line as well as vertical line, and this hashed line, inclined hashed line, supposed to represent that volume surrounding that particular node. And you can extend this everywhere, and the procedure is same or almost similar for unstructured grid also. In finite volume formulation, we use integral form of the governing equation, and it is given as integral over surface flux for a particular surface and equal to first term on the right hand side is for diffusion, and second term on the right hand side is for all the source term accounted, and this is integrated over the volume and this is integrated over the surface. Now, when we are writing finite volume formulation, the surface integral as well as volume integrals are approximated using appropriate formula, and we are going to see them in detail in subsequent lectures. Before we go into the details, we have to get familiarized with terminologies with regard to finite volume mesh, and they are same for 2D as well as for 3D. What is shown here is a line which represent 1-dimensional mesh, and you have all this dotted circle. These are nodes along that 1-dimensional grid. P is a point of interest, and W E, that is capital letters W E, similarly capital letters W W and E E are to represent nodes, and then you construct a control volume between nodes. So, for example, between P and capital W there is a control surface, and this is referred as small case w. Similarly, between node P and capital letter E, which is on the east side node. A control surface is constructed and that is referred by a small case letter E. Now, we have to know distances between node and face and node and surrounding nodes. So, because it is one dimensional, we have delta x, and delta x, this is between node P and west face W. So, we use delta x subscript P capital and small case W. Similarly, the distance between node P and the east face E is given here as delta x subscript capital letter P and small letter E. In the same way, distance between node to node. So, for example, in this case between node P and E is given as delta x subscript capital letter P and capital letter E. Similarly, for other side. Now, this west of west is referred as WW. Similarly, east of east is referred as EE. These are required in case you are deciding to have higher order accuracy scheme. In general, the Navier-Stokes equation, if you neglect unsteady term and convection term, then we obtain diffusion equation, and that is given here as divergence of gamma gradient of phi plus source term equal to 0. So, this gamma is a diffusion coefficient depending on the equation. Suppose if it is a temperature equation, then this corresponds to diffusion coefficient corresponds to temperature equation, and phi is any property. The control volume integration of this equation results as integration over the control volume divergence of gamma grad phi dV plus integration over the control volume source term dV equal to, and this we are converting volume integral to surface integral, and that is what you are seeing on the right hand side. The source term is left as it is because it is integrated over the volume and we take average. So, area integral gives the flux entering or leaving the control volume. So, in this case this n dot dA, dA is a area vector and n is a vector normal to that area. So, this will give actually the flux either entering or leaving, and the volume integral on the right hand side gives source term over the control volume, that is what is shown here. Now, let us see how to actually apply this equation for the mesh detail that we have shown. So, this is a equation and we integrate it. The mesh and corresponding details are reproduced here. P is a node of interest and we go from P to the left on the west node and to the right on the east node. We apply this integration for this mesh that is shown, and we get here gamma A d phi by dx evaluated at east face, that is here, minus gamma A d phi by dx evaluated at the west face, that is here on the left side. Because it is one dimensional, we are using d instead of dou, and the source term is evaluated as average over the surface over the volume. So, it is S bar delta V. Now, this is generalized form. So, in one dimensional you actually do not have V, but this is generalized form. A cross sectional area of the control volume and S bar is the average value of the source term. Now, let us see how to evaluate each of this term for the mesh that is shown here. For example, gamma A d phi by dx at east face, that is on this side. Similarly, gamma A d phi by dx on the west face, that is on this side. Suppose you happen to solve like this, then you get phi evaluated at node P, similarly at node E, EE and so on, similarly on the other side W and WW and so on. So, phi is variable that is evaluated only at the nodal location, whereas d phi by dx is a gradient of phi which is required at phases. So, in this case it is required at east phase or at the west phase. So, discretized equation are written on the cell faces, that is what we have just seen, but we know the values of the properties only at the nodes. So, P, E, W, EE and WW and so on. However, they need to be interpolated to get values on the faces. There are many interpolation methods available. We will choose initially a central approximation, that is gamma at W phase here is evaluated from gamma available at P node and gamma available at W node as an average. So, that is why it is gamma W plus gamma P by 2. Similarly, gamma at the east phase is evaluated from gamma available at east as well as at the P node as a central approximation gamma E plus gamma P by 2. Now, this gamma is a diffusion coefficient I mentioned before. In general, it may be fixed, in other words it may be constant, it may not vary for some cases, but later you will learn gamma also as a function of temperature or as a function of the flow. In the case of two phase flow, it may vary from phase to phase. So, here we are actually talking about a general procedure. The next term in the discretized equation is gamma A d phi by dx at W. So, we write this as gamma W A W and this d phi by dx at west phase. So, we know the function value at P node, we know the function value at W node, again use approximation between these two nodes and we get phi P minus phi W delta x P W as shown here. That is the distance between node P and node W, that is what is shown here. We write similarly for other phase gamma A d phi by dx at east phase as gamma E A E, again phi E minus phi P by delta x evaluated between the nodes P and E, and that is what is shown here as delta x P E. Again the question is about A. If it is a uniform mesh, then A will be the same, that is whether it is a east phase or west phase. We are writing here generalized procedure, that is why we still use a subscript E and W. So, for a situation when the control volume shape is changing from one phase to another phase between node to node, then this A can be used accordingly. This is again we are assuming a uniform mesh arrangement, that means distance between P and W, distance between W and WW, similarly on the other side distance between P and E or distance between E and EE are same. In such case the weightage are equal for both from both the sides for contribution at particular phase. For example, phi at P and phi at W will contribute same for evaluating phi at control surface W. Similarly, the other side. If you are having a non-uniform mesh arrangement, then you have to take weightage accordingly, and we will see that little later. Now, the source term is usually a function of a dependent variable. In this case, it is phi itself, and it is approximated in the linear form as source term average multiplied by delta V equal to S u plus S p plus phi p, and S u is a constant value and this is a linear variation. We have seen individually details now we have to substitute in the discretized equation. This was a discretized equation. We have seen how to evaluate each of this for each phase. So, we will substitute, we get gamma e A e phi e minus phi p delta x p e, similarly other term, then for source term. So, the equation now is a discretized equation of the diffusion equation by following finite volume procedure. We put all the things together. This was the original diffusion equation and we get a discretized equation. These are evaluated for the node that we have defined and we get final discretized equation in this form. We can observe in this equation phi p is a variable interest, p is the node of interest and you want to evaluate phi at the node of interest p, and you find the term appearing in the first term, appearing in the second term, also appearing in the last term, that is for the source term. This is a node, this is a variable at the node of interest. So, we need to collect that coefficients. So, collecting similar coefficients together as, so in this case phi p, then you write down all the terms corresponding to phi p together. So, you get gamma e A e by del x p e, that is what is coming here as a first term. Similarly, this term is here and then phi is also there, and this is a quantity of interest. So, you retain that on the left hand side, that is why some minus sign and plus sign gets changed when you move from left to right. Then remaining terms are in this equation phi e and phi w. Again you group those coefficients properly. So, phi w is written here and phi e is written here. Constant for source term S u is written separately. Now, if you look at the equation, for the moment you imagine terms in the bracket as one coefficient. So, some coefficient into phi p equal to some coefficient to phi w plus some coefficient phi e plus S u. Now, the mesh that I have shown, p is the node of interest, it is at particular instant or one particular location in the space. You can imagine the pi is running from left to right in the case of 1D, that is all the nodes of interest are going from left boundary to right boundary, then this equation is repeated for all the nodes from left boundary to right boundary. Now, if you can understand, this is the point of interest and phi w and phi e are known either from previous iteration or from the current iteration. That is why left hand side is unknown and right hand side is known quantity. Rewrite that equation again. As I mentioned, all the bracketed terms can be written as one value and that is shown here as A e, A w and A p, and A e is actually the term corresponding to east node gamma e by del x p e A e. Similarly, A w is a coefficient corresponding to west node, that is shown here. Now, you can observe that this term, the first term for phi p is same as term for east node, right. So, if you look at this gamma e by del x p e A e, this is the first term for phi p and that is same as gamma e del x p e A e coefficient term for east node. So, that we have already defined as A e. Similarly, the second term in the phi p is corresponds to coefficient term for phi w and that is what is shown here. So, coefficient for phi p can be rewritten in terms of these coefficients and you see here A w plus A e, the only term is not represented in other term is S p and that you can add separately here. So, this is actually advantage because you evaluate AE and AW, and that is good enough, and that can be used even in AP also. So, in terms of these newly defined coefficient, the discretized equation is written as AP pi p equal to AE pi e plus AW and phi W. So, it is so simple, and as I mentioned before, node P, which is a point of interest, it is just a representation. So, for a 1D it will run from left boundary, which is already as a boundary condition, node immediate to the left boundary all the way up to node just before the right boundary. So, P will run from that leftmost node to the rightmost node, then these discretized equation will become system of equations, and you can represent it in the form of a matrix. We have to have some procedure for inverting that matrix. Once you invert the matrix, then all phi p's are coming to be known. Such a procedure is solving the linear equation system, and we will have a separate class on matrix inversion procedure. So, near boundaries, in the case of 1D case, for example, the coefficient A W is actually west to the node of interest P. So, near boundary P will be one node very next to the left boundary, and for that node there is no west node, because the west surface is the left boundary itself. In such case, the coefficient A W is made to 0. Similarly, on the right side node very next to the boundary, there is no east node for that boundary, because east surface is a boundary condition itself, is the location where boundary condition is enforced. So, there is no east node, hence for the right boundary node near the right boundary AE is made to 0. You can imagine how it will be for the case of 2D and 3D. We will explain that in the subsequent slide. We have Navier-Stokes equation and definitely continuity equation. What we have seen is just one term in the Navier-Stokes equation, that is a diffusion term. We will see how to do for continuity equation, finite volume formulation for continuity equation. Let us take 1D steady incompressible situation. The continuity equation is written, because it is 1D, you can write it as d by d. So, d by dx of rho u equal to 0. Of course, it is incompressible. So, rho will not be there, it becomes only du by dx equal to 0. Again we have the same definition of node, control volume, distances defined for 1D case. Now, if you write integration of this equation for the control volume formulation, then you get rho u a evaluated at east face minus rho u a evaluated the west face, because its continuity equal to 0. It is very simple. Now, this rho is again for incompressible flow, it will not be there, it will come out, and the term itself will not be there, and if it is constant mesh, then A also will not be there, it is just only u at east face minus u at west face equal to 0. Of course, in 2D we will have a velocity in vertical direction, that will become v corresponding to the top as well as bottom. We would like to get a feel of how this is actually implemented. For that, we take one heat diffusion equation, one dimensional steady state heat diffusion equation as shown here, d by dx of k dt by dx plus s equal to 0, where k is a thermal conductivity, and for the problem that we are going to explain, k is given as 1000 watt per meter Kelvin, and area is 0.0001 meter squared, and there is no source term. That is a very simple situation without anything, it is just a heat diffusion. Problem figure is shown here, this is a cross sectional area, that is what is shown here, and boundary, left boundary value is also given, temperature at left boundary as 100 degree Kelvin. Similarly, boundary on the right side, that is B, T at B as also given as 400 degree Kelvin, and the distance between left boundary to the right boundary is 1 meter. Now, we divide the length of the rod into 5 equal control volumes. So, 1 meter divided by 5 will give delta x equal to 0.2, and that is shown here. So, this is the left boundary T A 100 and this is the right boundary T B 400, and define 5 equal control volumes or 5 nodes. So, 1, 2, 3, 4, 5, and for representation we are showing one control volume which is in blue color, and distance is uniform between any two nodes. So, delta x is same between node 1 and 2, and it is same between node and 2 and 3. Similarly, for other nodes. Near boundary, for example, left boundary, distance between node 1 and the left boundary is half, because we are having a uniform mesh, it becomes delta x by 2. Similarly, distance between node 5 and the right boundary is again, because we are following uniform mesh, it becomes delta x by 2. So, the grid consists of 5 nodes, and you are able to distinguish node 2, 3, 4 are internal nodes. Node very near to the left boundary is node number 1, node very near to the right boundary is node number 5. We have the discretized form of the equation, because only a diffusion equation, and for the variable temperature it is written here K E by del x P E A E plus K W by del x P W A W, and we mentioned there is no source term. So, that term is not appearing for the coefficient temperature P. Similarly, coefficient term for temperature evaluated at west node, and coefficient term for temperature variable evaluated at east node. As I mentioned before, this node P will run from left to right. In this case, it will run from 1 to 5. So, but node 1 and node 2 are near the boundary. For the moment, we will consider only 2, 3, 4 internal nodes. So, this equation is written for each internal node. For example, if you write the equation for 2, then T W actually becomes T 1 and T E becomes T 3. Now, repeat this procedure for 3 and 4. Okay. The discretized equation for nodal point 2, 3, 4, and you get generalized form A E A W A P. As mentioned before, it is K by delta x A, K delta x by A, and this is summation of other two coefficients. In this case, diffusion coefficient is constant, A is 1D is also constant, and delta x is also same. Hence, it happens to be a very, very simple case. Near boundary nodes, that is for node 1, the west side is boundary A, and we have the equation modified as K A T E minus T P by delta x, because for the node 1 each side is available, hence we write full term, whereas on the west side only half is available, that is delta x by 2, and west side you have a boundary condition imposed, that is referred here as temperature at A. Okay. So, that is also used here, T P minus T A by delta x by 2, and K A, this is diffusion coefficient is set to 0. So, in today's class, I have explained how to do for a diffusion equation, finite volume procedure for a diffusion equation. We understand terminologies used in finite volume mesh, and we are able to get approximation on east phase and west phase. we are able to understand how to deal for a boundary nodes, what term goes to 0 for the left side and right side. And to get some more understanding of this formulation, we started with one example problem, discretize the geometry into 5 nodal points equal distance. We could do internal nodes without any difficulty. There is a special treatment for boundary condition location node, and we explained for left boundary node, that is node 1, there the control surface to the left of node 1 is A, temperature condition at A is given, and we see how that finite volume formulation gets reduced for the left boundary. So, next class we will continue this problem and get idea of how to do for the right boundary, set up the complete equation including the boundary nodes, and how to solve the final one full matrix. And we compare with the exact solution. We will also see how to extend this procedure for 2D as well as 3D. With this I conclude today's class. Thank you.